Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to cover question number 4, what is mass? You can't imagine how many times I've heard people sitting around and talking to each other discussing this idea. Many have their own definitions and their own ideas about it, but today I'm going to talk about what the particle model says about mass. But here's the Wikipedia definition. Mass is both a property of a physical body and a measure of its resistance to acceleration. That is, a change in its state of motion when a net force is applied. So there's two things here. One, it says it's a property of a physical body, but the particle model going to emphasize that it is not a physical property. As it doesn't say that here, but it leaves it open as to whether it's physical or, in terms of the particle model, I claim it is an assigned property. We assign the value of mass, the concept of mass, to an object. The value of the mass is assigned by humans. We assign the value of my mass or yours or the mass of the Earth based on the 1 kilogram standard. There is a specification for building a 1 kilogram object. It's 90% platinum, 10% iridium, and then it's got a special shape, a special size, volume. And when we get all done building it, we take a Sharpie and we write on it 1 kilogram. If that's not assigning a value of mass to an object, I don't know what is. And then we compare that to our mass to this 1 kilogram standard. Now, the second part of this actually comes from Newton's second principle. It says it's a measure of the resistance to acceleration. So Newton's principle, if you read it, says that acceleration is proportional to the applied force, and divided and is inversely proportional to mass. So if you increase the mass somehow the mass increases. It's harder for a force to give it acceleration. For a constant force, you can't accelerate it as much. If you decrease its mass, it's easier to accelerate it. That's where this statement comes from, Newton's second principle. So the TPM definition, man is not real. Let me say that up front. Objects are real and objects move. Motion is real. We can observe motion directly. So my definition, or the TPM definition, is that mass is a concept applied to an object that helps describe motion. That's what we use it for. Otherwise, there's no apparent reason to give it an object this property. A change in motion is caused by two objects interacting with each other. It's the way you normally get a change, is that two objects interact and they each apply a force to each other. Okay. Now there are other types of mass that are talked about. In relativity, we have rest mass and relativistic mass, and it comes right out of the equation for mass from special relativity. The mass of an object moving at velocity v is equal to its rest mass divided by this square root of 1 minus v squared over c squared. And the rest mass, if you want to know what the rest mass is, you set velocity equal to 0, and it's going to be, the result is m sub r, mass at rest. And if you want to know what mass is at the speed of c, well, then you got 1 minus 1 in the denominator under the radical, and now you have something that can't be determined. It's indeterminate. But when I explained the value of mass as defined by the 1 kilogram standard, there was nothing in there about velocity. It didn't matter whether we did this on the Earth or we did it on a spaceship, we'd still label it 1 kilogram. The velocity doesn't have anything to do with the value we humans assign, but relativity would like you to believe something different. Of course, I'm not a relativist. Now let's talk about mechanical mass, and this really comes strictly from Newton. Inertial mass is usually associated with Newton's first principle. If an object of mass m is moving at constant speed, Newton claims that it implies that it has inertia. And actually, we define, this is an equation that we humans define momentum as mass times velocity to give us some figure of merit of that momentum and an implication of what the inertia is. The change of this velocity is described by his second principle. I'm just rewriting the equation a different way. So the acceleration is a change of velocity, but you got to apply a force to get acceleration. You can't have acceleration without a force. Both of these values, both this m and this m, are generally considered inertial mass. Gravitational mass comes from his gravitational formula. Small m appears here, and appears there. The small m in the gravity equation was literally taken from this one. If you want to develop this, and you can do it, I've done it, you can develop it, but you use this equation and you put this. So it starts out here as inertial mass, moves into here, all of a sudden now it's gravitational mass. But from a nomenclature point of view, it's the same m. It didn't. Nothing made the object different. Same m comes from that equation, is put there. Okay, but Newton says is the one who comes up with the idea of inertia. He says it's the vis insita, or innate force of matter, something in the object that keeps it going at constant speed in a straight line. It's inherent in the object itself somehow. The particle model says, yeah, it's true in open space. If there is nothing to slow the object down or to speed it up, it will keep going. But the particle model claims that space is not a total vacuum. There is a G1 particle field out there all the time. And your object, whatever you're thinking about moving through, with mass m moving through space, is constantly being bombarded, hit by G1 particles. But this is a sustaining force. An object in outer space not close to any large object will have G1 particles hitting at it from all directions. It will keep the object moving at constant velocity and constant direction. Well, I say that with a little bit with tongue-in-cheek. G1 imposes an equal force up and down, left and right. Pushes left, pushes right, pushes up, pushes down, pushes forward, pushes backward. Well, except for backward. The direction of velocity, in a mechanical sense, the G1 particle will push harder pushing back than it does pushing forward. So there's some drag. Maybe not so much constant velocity. It's the speed difference that makes this virtually imperceptible. This drag is very small. Any other force that interacts with the object must overcome this sustaining force. So if you want to move the object, you've got to overcome the G1 force, or what we call inertia. So I'm saying that the G1 force field is a sustaining force that is the cause of inertia. Well, let's go on to something else here. Einstein's equivalence principle. This is a thought experiment that Einstein gave us, and it goes this way. There is no experiment, he emphasized that, no experiment that will discern the difference between the effect of gravity and the effect of acceleration, or, to say it another way, gravitational mass and inertial mass are equivalent. That's what he says. Personally not objecting to the statement except up here where he says there is no experiment. Einstein says there is no experiment that will discern the difference between the effect of gravity and the effect of acceleration. If the only thing that can be detected, and this is somewhat where Einstein kind of leads us astray, he puts you in an elevator, and he assumes you don't know that you're in an elevator, and he puts you in that same elevator room on a spaceship, and he assumes you don't know this, so he's putting blinders on. And so he implies the only thing that can be detected is the compression caused by gravity or caused by acceleration. And then we are led to believe that we can't tell the difference. David told me he did not agree with this Einstein's thought experiment. He said this recently. But he says, isn't there a way for us to discern the difference? Engineers to the rescue. Well, unfortunately, I'm not giving you a specific experiment, but I'll give you some ideas anyway. Number one, the force on the Earth is pushing down while the force on the spaceship is pushing up. Well, there's more to this, and I get into it right away here after this slide. But the net moving force on the man on the Earth is pushing down, and the net moving force is pushing up, and yet the acceleration is claimed to be in the same direction. I didn't make that point earlier. I probably should have, but the forces being opposite, but the acceleration being in the same direction, seems to me implicitly saying that this is not true. But if you're in a room or an elevator and you don't know where you are or what's happening, you might not be able to know the difference between where the direction of the force. Nonetheless, it's a point to follow up on. One of the main points is vibration. There is no vibration in the elevator on the Earth, unless there's an earthquake nearby. Well, there is vibration on a spaceship due to the rockets. Okay, Einstein could invent one that has no vibration, and we could counter it that way. But under normal circumstances, if you're going to have a force that's going to accelerate you at a value of g, constantly pushing you, accelerating, you're moving faster and faster and faster. And you're using rockets to do it, as the picture shows, surely you'd feel that. Okay, so gravity using TPM. Let's talk about gravity and how we feel it, because you're a man inside here. You're a man sitting inside this room. You're on the, and there's the acceleration is pushing down, and the G1 particles are pushing down. G1 gravity says there's more G1 particles pushing down than pushing up. And yet there are G1 particles pushing the Earth up and the man down. So when I write equations for the force on the man and then write equations for the force on the Earth, I get that the forces are equal. They're equal and opposite. And if the force is equal and opposite on you, if I can get my hands right, you're going to feel the compression. We feel the compression because there are opposing forces. Okay, inertia using it. The rocket ship is moving the spaceship with constant acceleration. The force is up, the acceleration is downward, while the G1 particle field is pushing back on the man. I made that point earlier. There is drag. The man's going to feel compression because there's the force pushing this way, and there's the drag pushing this way, and he's going to feel the compression. That's how we feel it in a very simple way. Is there an experiment to do this so we can absolutely prove where this guy is? Well, maybe that's another video. Okay, relativity states that inertial mass and gravitational mass are equivalent. But the particle model suggests they are identical because each individual interaction causes the same motion on the individual atom in the object, in the man in this case. The G1 particle is the same particle acting on the man in the elevator on the Earth as he is in the elevator on the spaceship. G1 interactions are identical. It's the same particle, it's the same man. They're going to be identical. The individual interactions are identical. The overall net effect is different because when you're on the Earth, you have a net force of gravity caused by an imbalance of the G1 particle field. That's because the Earth is there. With the Earth there, you have fewer G1 particles pushing up, and so the interactions are identical, but the source of what's pushing is not. There's an imbalance on the Earth. When you're in the spaceship, the G1 interactions, each individual particle interacts with the man the same way. But the source of the G1 particle is different. It's equal and opposite in all directions. And so then you have a situation that we call inertia. So should the mass be different if the interactions are identical? I claim that in relativity, not only is inertial mass and gravitational mass are not just equivalent, they are identical. Interesting thing, I've never talked about drop towers. They have been used to measure inertial mass, having objects accelerate in free fall. And by so doing, you measure the acceleration, and they get to mass, and that value of mass in free fall is always equal the measured value of mass using a gravitational scale. It's always been equal. Measured values, in a sense, Einstein's right, but he's trying to trick you into believing it one way, just because you standing there in the elevator, you can't see, you can't hear, you can't feel, or whatever, you're totally handcuffed. I'm saying with the particle model, that's not true. I can give you an exact reason using the particle model why the inertial mass and gravitational mass are identical. So anyway, this is the conclusion. Mass does not change with velocity. What kind of physical mechanism changes the value of mass when an object moves at a different velocity? There is no explanation for why velocity changes mass. Inertial mass and gravitational mass are not just equivalent, they are identical. The G1 particles interact the same way with atoms and molecules in a given object. Therefore, the individual forces are the same, and therefore the sum of all the forces are the same given the same environment. Earth environment and space environment are different. Mass is not a physical property. It's an attribute or an assigned property to an object that helps us describe motion. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.